Today we start our study on acids and bases, and this is just a 2-week study. This week we're going to focus on definitions and properties of acids and bases, and then next week we will calculate the pH and the pOH to measure the concentration of the acidity and basicity of our solutions. So first we want to look at acid-base reactions. And an acid-base reaction is a reaction between hydrogen and hydroxide compound that form salt in a water. So it's really a double replacement reaction, or a special type that we call a neutralization reaction, because it forms water and some sort of ionic compound that we call salt. So we have between an acid, which has H hydrogen ion, and base, OH. This is kind of our first time looking at this definition of acid and base, but H containing compounds will be acid and OH containing compounds will be base. In this reaction, they're going to neutralize. So it produces water as a result. Whenever we are characterizing acids and bases, we'll start to see some similar patterns in their properties. All things that are acidic tend to be sour. They also tend to have low pH. Actually, all acids have low pH, and they contain the hydrogen cation. When acids and bases are introduced to water, actually all of them are going to be acidic or basic solutions, so they will be in water. Those H's or hydrogens are going to bond with a water and form what we call a hydronium ion. So that's H and H2O kind of bonding together to form H3O if you add those together. This is a hydronium ion, and that will be part of our definition. In water, it produces hydronium, H3O, positive charge. Now, some indicator responses. Indicators are solutions that we can add to acids and bases, which will give us information about their acidity and basicity. So if we have a solution and we're not sure if it's an acid or a base, we can use some indicators. So I'm going to write down here our indicator responses. We are going to focus on 3 indicators. We have litmus paper, and if you put litmus paper into a solution and it turns red, then it's an acid. And we also have universal indicator, which shows like a rainbow spectrum, if you will. And so red, orange, and yellow will be on the side of acid. Red is really low pH, and then yellow will be getting higher. And then at green, that's more neutral, and then it'll become more basic. And then the other indicator is phenolphthalein. It's a fun one to spell. Okay, let me try that again. Phenolphthalein. Okay, and that's our third indicator, and it will either stay clear or turn pink. For a base, it will remain clear. I'm sorry, for an acid, it will remain clear. For a base, it will turn pink. So let's go ahead and write those responses for base. So we've got litmus paper, same thing, will turn blue. Universal for a base is green, blue, and violet. And phenolphthalein is pink. If something is neutral, it will be purple from litmus paper because it has kind of both acid and base properties present, because a neutral compound has H and OH. So litmus paper will turn purple, universal indicator will be around green, and phenolphthalein will stay clear. So some base properties. Bases, the ones that are safe to taste, will taste bitter. They have a high pH. And they contain the hydroxide ion. That's our OH. That's going to be our anion. Okay. And we already talked about those indicators. Bases will tend to have like cleaning properties, so soaps are basic in nature, and some bases don't always have hydroxide anion. It depends on which definition we're using. We're going to talk about here in a second. So we have two different scientists who have defined acids and bases, and the most basic definition that we've already discussed is called the Arrhenius definition, that acids have the H cation and bases contain the OH anion. Okay, so looking for H and OH. Example 1 is using the Arrhenius definition, so we're just going to label them acid or base based on does it have H or does it have OH. So our first one, we have OH, so that would be an Arrhenius base. All right, A, B. The next one we have H, and then here's the anion, that's acetate. So this looks like it is an acid because it has H. We got OH again, there's a Arrhenius base, OH, base, H, acid, OH, base. You do the rest, you get the idea. It's pretty straightforward. If it has H as the cation, it's an acid, and if it has OH as an anion, it's a base, according to the Arrhenius definition. The Bronsted-Lowry definition is a little bit broader because the scientist realized that bases can exist that don't just have OH. As long as they are going to be accepting a hydrogen within the reaction, then they can be considered a base. And so this one's a little bit more of a broader definition. Our acid is still going to have that H, so we call this a H donor. And that fits the same definition as Arrhenius, it's just worded differently. It can only donate if it has H. And then the base is an H acceptor. Conjugate acid and conjugate base, those are just referring to within an acid-base reaction. The conjugate acid is going to be the H donor from the product side, and the conjugate base is the H acceptor on the product side. So let's try our hand at these because it's a little bit, like I said, broader. It's not as straightforward of a rule. So we have to think about where the hydrogen is moving in order to determine acid or base. And we will have a full reaction in order to figure out where the hydrogen is moving. So in each acid-base reaction, identify each reactant as a Bronsted-Lowry acid or Bronsted-Lowry base, and then each product as a conjugate acid or conjugate base. The best way I like to approach these problems is to just look at kind of our before and after and see where the H moved. Also, you'll notice that there's this double arrow in the middle here. That just indicates a different type of reaction than we've studied thus far in the year. That indicates a reaction that is actually able to go both directions. It's reversible, and we call this an equilibrium reaction. And that's really as deep as you need to know right now of that double arrow. But for our purposes, we're going to call the left side still reactants and the right side our products. And we're just going to look at our before and after and see where the hydrogen moves. So we start with water, and its kind of similar partner, I'm going to label those with stars, is H3O. It's changed by just one hydrogen. And you'll see, label the second one with a circle. These two are also kind of partners, if you will. They're only different by a hydrogen. We have C2H3O2 with an H and C2H3O2 without the H. So the two that I've marked with the same symbol, those are our partners or our pairs. We call them conjugate acid-base pairs. So let's take a look at how the hydrogen moves. It looks like we're going to be taking this guy and moving it over here in order to make this product occur. Because our stars, we're kind of gaining a hydrogen on the product side. So that means our C2H3O2 is the donor. So this is our Bronsted-Lowry acid. And our H2O is the acceptor. It's going to take it. Bronsted-Lowry base. And then we'll do the same thing. If we were to flip the reaction over and see, where did the hydrogen move now to get back to where we started, we're going to do the opposite. So our H3O, that's our conjugate acid. It's on this product side. And that would make this guy our conjugate base. So just look at where did the hydrogen move to get from one side to the other of the reaction. Our next one, we're going to ignore the lithium. That's just kind of a distractor, and we're crossing it out because it's on both sides. It would be what we call just a spectator ion. So the actual reaction is written with them as just the ions. So let's again kind of look at the pairs and see where the hydrogen would move. It looks like our H would be moving here. And then to get back the other way, our H would be moving here. So this is our Bronsted-Lowry acid, because it's giving it, donating it. And this is the Bronsted-Lowry base. This is the Bronsted-Lowry acid and the Bronsted-Lowry base. I'll let you do the last one, and then we're going to answer these questions together. If a compound is an acid, it fits Arrhenius, Bronsted, or both definitions. Well, they're kind of the same definition because they both require an H, so both. Any base with OH fits Arrhenius, Bronsted, or both definitions. Both. Because even here, see, we have OH, and we still have a base, so it works. It can be that hydrogen acceptor. Any base without OH fits, well, it's not going to fit Arrhenius, so that's only Bronsted-Lowry. And which acid-base definition includes more compounds? We talked about that as being Bronsted-Lowry, the broader definition. You have a practice page to kind of work through some of these Bronsted-Lowry acid-base, conjugate acid-base. Just look for the hydrogen and see where it moves. And then for 3 and 4, consider how it would work if you were to add or take away a hydrogen based on its definition. So if it's a conjugate acid of these, you're going to add a hydrogen. Conjugate base, you're going to take away a hydrogen. So just a little note to help you there. For their acid-base pairs.